we're going to explore a few things and look at some different vocabulary that deals with probability. So the first thing you're going to do is, this is my wardrobe here. And let's see. So for my wardrobe, I have 3 pair of pants. I have 5 different math t-shirts. And I have a black pair of shoes and a brown pair of shoes. Okay? So this is Mrs. Hyatt's wardrobe. All right? What I want you to do is I want you to list the possible outfits that I could wear. Okay? So the possible outfits that I could wear. So you are probably going to want to, instead of writing a word for each of these, label the pants like J, K, and B, or something. Make yourself a little key there. The shirts, you could probably go by color. I think, well, that one's gray and that one's white. Yeah. Let me do entire page so you can see a little better. Okay. And I need you to come up with all of the possible outfits I could wear. I assume I must wear pants, a shirt, and shoes. I'm not allowed to come to school without any of those 3 items of clothing. Can't come to school barefoot.
So you want to write every single outfit?
Yes. I want to know what they all are.
Oh.
But that's a good question. Can you multiply? I remember something like that. Can you multiply all the numbers and give you the number of outcomes so you can make sure you've got them all? I need you to list all the outcomes for me. So you can't, like, I want a list of all of them, but would that give you the number you're supposed to have? Would it? It's a different, like if I have the same shirt and same pants but different shoes, it's a different outfit.
Oh my God.
So I can pause it here. This is called our sample space. And Kayla was right. To know how many solutions you have, you can take, you've got 3 pair of pants times 5 possible shirts times 2 possible shoes. So you're going to have 3 times 5 times 2 is going to give you 30 possible options here. These are all of the possible options. I use J, K, and B for jeans, khakis, and black. I just numbered the shirts 1 through 5, and then I use BL for black shoes and BR for brown shoes. So you may have chosen something different, but you should, in some, except for that right there should be a K, shouldn't it? So in some systematic fashion, you should have figured out all of these different possibilities. Okay, so this is called the sample space for this particular instance. So the next one you're going to look at there says if Mrs. Hyatt gets dressed in the dark. So I'm just like choosing things without it being able to actually see them. Assume it's pitch black dark, and I can't tell the difference. So if I get dressed in the dark, what is the probability that my outfit will look like this? Okay, that is one specific outfit. It is the only one outfit that will look like that, so that would be 1 out of 30. Okay? Okay. What is the probability that if I get dressed in the dark, my outfit will look like this? Or will include these items, I guess. Because what am I missing here? Shoes. So I could have this outfit with black shoes or this outfit with brown shoes. So 2 out of 30. Or we could reduce that to be 1 out of 15. So there would be a 1 out of 15 chance that I would come to school with this outfit on. Okay. What about the next one? What's the probability that if I get dressed in the dark, my outfit's going to include khaki pants? Okay. It is going to be 10 out of 30, which does reduce to 1 out of 3. Okay, so we're familiar with probability. These things should hopefully be familiar to you. All right, so let's look at some vocabulary. We have experimental versus theoretical probability. Okay, experimental probability is based on observations from an experiment. Okay, theoretical probability is based on reasoning. Okay, so we're going to do a quick simulation here. Okay, I need everybody to get a coin. You don't have one of them. You need a coin. Raise your hand. I'll bring here. Okay. Alright, I want you to flip your coin 10 times. Record the number of heads you get and the number of tails. Flip it 10 times. Flip your coin 10 times. Record heads or tails. And that would be 103 out of the total number of flips, which was 200. If you've already written yours down there, that's fine, but put the class total with it. So we've got 103 divided by 200. That is 0.515 if we do a decimal. Okay, so 0.515 is our experimental probability. So should we go around telling people that if you flip a coin, you've got a 0.515 chance of getting heads? Okay? Why not? What should it be? Just by reason, your probability should be 1/2 or 0.5. Right? Because there are two sides of the coin that are equal. You should get 50-50. We were pretty close to 50-50, but not exactly. All right. So we had experimental probability was 0.515, and our theoretical probability was 0.5. Okay. So if everyone in the whole room flipped a coin 100 more times, what do you think would happen to our experimental probability? We don't have time to do this, but okay. David says it's going to get closer to exactly 0.5, right? Exactly 50%. And he is correct. So if we flip, like if everybody in here, if I had you guys flip a coin 100 times, then if we added those together, it should be closer to 0.5. And then maybe if that didn't work, I could have you flip it another 100 times. And then that should be closer to 0.5. This is what we call the law of large numbers. And it is really important to any type of probability. The law of large numbers says as the sample size increases, experimental probability should get closer to theoretical probability. So I will give you the example that I use often. My sister-in-law and my mother-in-law, both of my sister-in-laws and my mother-in-law, they will make the claim that Hyatt men only have boys. We can't have anything but boys in our family. Now, here's the problem with their claim. I have 2 kids. My brother-in-law has 1 kid. My sister, my husband only has 1 brother. His sister was adopted from Russia. First of all, it wouldn't even matter if she was adopted or not because the male determines whether or not it's a boy or a girl. The female has nothing to do with it. So it would make no difference since she's a girl anyway. But she was adopted. So she has no genetic ties to the Hyatts anyway. So, you know, although she's very much a part of our family, it doesn't make any sense to include her in our data. So I have 2 boys, and my brother-in-law has 1 boy. We have a sample size of 3. Now, if we had 30 kids between the 2 of us, and 28 of them were boys, then that would start to become significant, right? But with a sample size of 3, we cannot make the claim that Hyatts only have boys, because that is ridiculous. I've tried to explain the law of large numbers to them when they make this comment, but they still make it. Well, you know, if we had another one, it'd be a boy, because we can only have boys. You're right. And my brother-in-law says he's only having 1 kid, and I probably not going to have any more, so we were going to remain a sample size of 3, so I guess they're just going to keep claiming it over and over. But whenever you have really small sample sizes, you can't make generalizations about things. That's why whenever you flip a coin, if you flip a coin 3 times, it's pretty common to get 2 out of 3 heads or tails, or maybe even 3 out of 3 heads, right? So if you got 3 out of 3 heads, you would say, oh, this coin can only flip heads, right? That would be a ridiculous statement to make. That's pretty much what we're claiming whenever we say that Hyatts can only have boys, that we flip 3 heads in a row, and that means that that coin will only flip heads. So if you want to make generalizations about something, you have to have a much larger sample size. So like I said, if there were, 30 kids between the 2 of us, and a huge number of them were boys, then our claim might be supported a little bit more. But most of the time, it's really not even statistically significant. Lots of different things operate off of the law of large numbers. For example, you may know someone or have at least heard of someone who has won big money in a casino, right? Let me tell you that if you go to a casino, you are probably not going to win a lot of money, because the casino has to make money. And how does the casino make money? It takes in more money than it gives out. So yes, you're going to know they have to let people win, because if people didn't win, people would never go, right? If you never saw anybody winning, then you wouldn't go. You'd just say, oh, everybody's just wasting their money. Like I try to tell my son whenever he wants to put his money in the claw machines. He would play every claw machine between here and California if he could. And he would, in fact, it's so bad that whenever we go by the one in Walmart, my 2-year-old says, "Hun'll waste money?" and points at the claw machine, because that's what I usually say. But he would keep feeding his quarters to the claw machine forever for the little $2 stuffed animal in there. But the law of large numbers operates in the favor of a casino, because yes, they're going to lose sometimes. Sometimes they're going to lose big. But they have worked out the probability, so they've got it set in their favor. So whenever a big casino in Vegas has, you know, thousands and thousands of people come every year and spend a bunch of money, they know they're going to come out on top because the law of large numbers tells them that they will. So, so it's really important for statistics. So let's go back to what we were doing at the beginning, right? So based on what we have here, which I've kind of already got for you, what is the experimental probability that you will win if you switch? So based on our experimental probability here, we won 10 times out of 15 if we switched, which is 0.6 repeating, 2/3 of 0.6 repeating. That's our experimental probability. Okay? Experimental probability that we win if we stay, right? If we win if we stay was 7 out of 15, which was 0.47. It's probably actually 4.6 repeating, but we'll just go ahead and round it there. Okay, so do you think we should make assumptions based on that? We did play like 30 times, but just 15 each. Do you think we can make big assumptions based on that there? If we played a lot more times, thousands of times, it should get closer and closer and closer and closer to the theoretical probability, right? So if we were able to do that a bunch of times, then we could rely on our experimental probability a lot more. All right, so the question I have for you that I'm not going to answer is, what is the theoretical probability that you will win if you switch? Okay, what do you think it should be? 2 doors, 1/2, 50-50? So ours here is just kind of like we haven't done enough trials for it to even out at 50-50. So that, you know, would be one logical way of looking at it. There is an answer to this, okay? I'm not going to give you the answer to this or tell you whether you're right or wrong. I'm going to give you some extra credit if you find and are able to explain to me the probability of this. Okay? You have to find it and be able to explain it to me. So you have to write down your findings and explain it in words and be able to answer some questions about it if I ask you. Okay? You can find it on the internet everywhere. Especially if you look for the Monty Hall problem, because he was the host that did this, you'll see it. Okay? So some extra credit if you figure that out. All right? But not extra credit